Hello everyone, welcome to my YouTube channel Decoder's Day. So today we are going to see the most important theorem. It is nothing but redundancy theorem. So we'll dive into the definition of this theorem. The definition says like that: in the given Boolean equation, if a variable is present in complemented as well as its non-complemented form, then the other variables which are there with them comes as a product term in the same equation, then the whole term is going to consider as a redundant term. Means thus definition says like that: if an equation there is, suppose a is a dummy variable, a is there, if non-complemented form is also there and along with that complemented form is also there, then the terms then the terms which are there along with a and a bar, if the product of this term is come in the same equation, suppose here is b and here is c, if the product of b and c comes in the equation, then the product term is going to consider as a redundant term. That means this can be neglected and can be written the whole equation as AB plus A bar C. This is what all about this theorem. So we'll solve some examples on the redundancy theorem. Okay. So first example is like, first one will be like A bar B bar plus A C plus B bar C. So this is the example. So first we need to check whether the variable is come in complemented as well as in non-complemented form or not. So which variable has come in complemented and non-complemented form? So see over here, A is here. A bar is there in complemented form and A is non-complemented form. Means A is come in both the forms. We'll check for B. B bar is there. B is not there in entire equation. So it is not applicable for B. We'll check C. C is in one form, that is non-complemented form. So we'll try to find whether there is redundancy theorem is applicable or not. So C or A bar is there, A is there. Along with that, which terms are there? B bar and C. The product of these two is present in third as a third term. So the term which you got over here, this is a redundant term. So the whole equation can be written as A bar B bar plus A C. Okay. Next, another one example. Second one example as A B bar plus A bar C bar plus B bar C. We'll see whether the redundancy theorem is applicable or not for this equation. Okay. First check which variables have come in both the forms. That means in complemented as well as non-complemented form. So A is present in both the forms. Okay. Here is non-complemented. Here it is in complemented form. We'll check for B. B is in non-complemented form in both the terms in entire equation. C is present in complemented as well as non-complemented form. So there is a possibility that redundancy theorem is applicable for in terms of C variable as well. So first we are going to check for A variable. A is present in complemented as well as non-complemented. The variables which are present along with A and A bar are nothing but B bar and C bar. We are going to check whether there is a product of these variables is present as a third term or not. B bar is there, C bar is not there. So there is no redundancy theorem applicable in terms of A bar, in terms of variable A. So next check for C. C is there. Along with that C, which variable is present? B bar. Along with C bar, which variable is there? A bar. So we'll see the product of this is present or not. Means A bar, B bar is there in whole equation or not. So there is A is there, B bar is there. So A bar, B bar, we were expecting, but there is no A bar, B bar. So there is present A, B bar. So there is no redundancy theorem is applicable. So redundancy theorem fails. Redundancy theorem fail. Okay. So there we can't do any manipulation in this whole equation though. So the whole equation can be written as it is. Okay. So we'll take another one example for it. Okay. So let's take third example as A is there. With that B bar is there plus B is there. C bar is there plus C is there. A bar is okay. In this equation, you can see all the terms which we have mentioned. Those have come in complemented as well as non-complemented form. So we'll check for each variables whether the redundancy term is present or not in this whole equation. So check for B. B is in complemented and here non-complemented. Along with that, these terms are there A and C bar. The product of this is not there in whole entire equation. So redundancy theorem is not applicable for B. If you check for A is here in non-complemented, it's in complemented. Along with that, B bar and C. B bar C product term is not there. If you check for C is there in non-complemented, it is here in complemented form. So A bar B we will need to find, but there is no A bar B term. So here also redundancy theorem fails. Redundancy theorem fails. Okay. So next example is like A plus BC plus A bar C. So we'll see whether the redundancy theorem is applicable and which way we can reduce this equation. First step, the variable is present in both the forms or not. Here A is present in both the forms. Okay, so redundancy theorem may be applicable. Next terms like B. For B is present in one form only. There is no any complement form of B. C is present in only one form. So we'll see redundancy theorem is applicable or not. Along with that A, there is no term, means 1 is there. 1. Along with that A bar, C is there. We are going to see whether there is C present in entire equation or not. Means 1 dot C is going to be C, right? So C is not there in the entire equation. So redundancy theorem fails over here. So there is another one way which can be helpful for solving this equation. So as we were aware how the plus operation is going to distributed over dot operation. So how it is going to be distributed for this whole term. It's going to be A plus A bar. In between this dot operation comes and A plus C. Okay. Plus BC will remain as it is. If you see A plus A bar, we have seen in our previous video. If you have not watched that video, you can go through that and come to this video. Then only you will come to know the equation A plus A bar can be written as 1. Okay. If you take the OR operation of the variable with its complement, the answer is going to be get as 1. Okay. Dot A plus C plus BC. Okay. From this equation, we can take C as a common. Okay. A plus, if you take C as a common, it's going to be 1 plus B. Here comes our OR operation related theorems. If you add 1 to any variable, so ultimately we are going to get 1 as a result. Here I am going to write it as 1 plus anything is going to give you the result as 1. Okay. So the whole term is going to give you as a 1. So 1 is going is dot operated with C. So A plus C dot 1 is going to give you A plus C. So this is our ultimate answer. Hope you got this. So if you are having any query related to this concept, you can post it into the comment section. Thank you. Thank you so much for watching.